NASA is saying the Voyager 2 probe is now in a space between the stars after exiting the sun's protective bubble, which is called the heliosphere.
When NASA confirmed that Voyager 2 had finally crossed the Heliopause, it marked one of the most significant milestones in the history of exploration. The Heliopause is the invisible frontier, the outer boundary of the sun's influence, where the constant stream of charged particles, known as the solar wind, finally gives way to the interstellar medium, the vast ocean of space between the stars. For decades, scientists debated exactly where this boundary might be, and whether humanity would ever be able to send a machine far enough to reach it. Voyager 2 has now given us that answer. Launched in the summer of 1977, Voyager 2 was originally intended to explore the outer planets, capturing breathtaking images of Jupiter, Saturn, Uranus, and Neptune, and providing data that completely transformed our understanding of the solar system. But the probe's mission did not end there. With each planetary flyby, Voyager 2 gathered momentum, flung ever farther from Earth by gravity assists, until it was set on a one-way journey into deep space. Now, more than 12 billion miles from home, the spacecraft has entered a region where the light of the sun is no stronger than a faint whisper, and where the rules of cosmic space begin to shift. This crossing makes Voyager 2 only the second human-made object in history to officially leave the solar system, following its twin, Voyager 1. But Voyager 2's crossing is particularly important because, unlike Voyager 1, its instruments were still fully operational and able to send back real-time data. That data confirmed what many had hoped. Humanity is no longer confined to its birthplace. A machine carrying the voices, sounds, and music of Earth has moved into the space between the stars. It is more than just a scientific achievement. It is a cultural and philosophical milestone. The golden record bolted to Voyager's side, carrying greetings in dozens of languages, has now officially entered interstellar space. This event also marks a new phase in human history. For the first time, we are receiving information from beyond the sun's protective shield. It is as if a diver has left the safety of the harbor and plunged into the open ocean. What Voyager 2 is about to encounter is not only uncharted territory, but also a realm filled with mysteries we could not have anticipated. And so, as it drifts silently onward, powered only by its decaying nuclear generator and ancient 1970s electronics, Voyager 2 reminds us that exploration does not always demand speed or power. Sometimes it is persistence, patience, and endurance that carry us the farthest. The spacecraft is now a lonely traveler among the stars, but with each transmission, it sends home. It delivers not just data, but a profound reminder of what humanity is capable of reaching. When Voyager 2 crossed into interstellar space, scientists expected to find a gentle, weakening magnetic field, something faint, diffuse, and fading with distance from the sun. After all, that had been the prediction for decades. But what Voyager 2 actually recorded was not weaker at all. It was stronger. In fact, the magnetic field outside the heliopause was nearly 3 times more intense than what Voyager 1 had measured years earlier. This discovery left scientists stunned. If the sun's influence truly ended at the heliopause, then the interstellar magnetic field should have been relatively uniform and weak. Instead, Voyager 2 revealed that space beyond our solar system is far more complex, structured, and dynamic than anyone had imagined. The probe wasn't moving into empty space. It was entering a region where unseen forces were shaping the very fabric of the cosmos. Before we dive into the astonishing discoveries of Voyager 2, hit that subscribe button and turn on notifications. You won't want to miss any updates from the edge of the solar system. And if you love exploring cosmic mysteries, strange phenomena, and hidden science, give this video a like so we know to keep bringing you these mind-blowing discoveries. Even more puzzling was the direction of the magnetic field. Voyager 1 and Voyager 2, though separated by billions of miles and traveling along different paths, should have detected fields pointing roughly the same way. Instead, Voyager 2 measured a field oriented in a different direction, suggesting the two spacecraft had not crossed into a single uniform interstellar medium, but into distinct regions with their own magnetic personalities. This forced scientists to reconsider long-standing models. For decades, the Heliopause was thought of as a smooth bubble around the solar system, a neat dividing line where the sun's magnetic field ended and the galaxies began. But Voyager 2 showed that the truth may be far more complicated. The boundary is not a simple edge. It may be twisted, folded, and even rippling, shaped by galactic currents and interactions we are only beginning to glimpse some. Researchers now suggest that Voyager 2 may have entered a magnetic highway, a filament-like structure, threading through interstellar space. These magnetic highways could act like invisible rivers, guiding the flow of cosmic rays, shaping plasma behavior, and even influencing how energy moves across the galaxy. Others propose that localized interactions between the solar wind and galactic magnetic fields are creating pockets of intense strength, like eddies in an ocean current. What is clear is that the solar system is not floating quietly in a uniform void. It is embedded within a galactic environment that is alive with structure, pressure, and movement. Voyager 2's readings challenge our very definition of where the sun's domain ends and where the galaxy begins. This discovery carries profound implications. If magnetic fields beyond the Heliopause are stronger and more variable than we imagined, then the radiation environment surrounding our solar system may be shifting all the time. As Earth orbits within this dynamic bubble, subtle changes in magnetic conditions could ripple through the solar system, influencing cosmic ray flux, atmospheric chemistry, and possibly even climate patterns on long time scales. Voyager 2 has revealed that the boundary between the Sun and the galaxy is not a wall, but a restless frontier. Every new piece of data forces us to rethink what lies beyond, and it hints that the galaxy may be full of vast, unseen structures, shaping the journey of stars, planets, and perhaps even life itself. One of Voyager 2's most surprising discoveries beyond the Heliopause was the way cosmic rays behaved. For decades, scientists believed that cosmic rays, high-energy particles streaming in from the galaxy, would arrive in a fairly uniform, random pattern. They imagined a constant drizzle of particles, steady and even, like rain falling on an open field. But Voyager 2 showed us something very different. Instead of a smooth flow, the spacecraft detected surges and pulses, as if the cosmic rays were being delivered in waves or bursts. At times, the intensity would spike suddenly, only to fall again, suggesting that these particles were riding along invisible currents of energy. This was not the quiet emptiness of deep space. It was a turbulent environment, structured and alive. Even more puzzling was a strange directional bias. Rather than arriving evenly from all directions, many of the highest energy particles seemed to be coming preferentially from one side. This was a revelation. It suggested that Voyager 2 was detecting the imprint of large-scale structures in the galaxy, hidden magnetic fields or gravitational effects that were bending and funneling cosmic rays like invisible lenses in space. Some scientists now believe Voyager 2 may have stumbled upon evidence of vast interstellar magnetic highways, channels that guide cosmic rays across the galaxy. Others propose gravitational lensing, where massive unseen objects, possibly even concentrations of dark matter, are warping the flow of particles and creating these biases. Whatever the explanation, the message is clear. Cosmic rays are not simply random noise in the universe. They are shaped, steered, and modulated by forces on a galactic scale. These particles carry with them the fingerprints of the environments they've traveled through: supernova explosions, magnetized clouds of gas, and perhaps even the scaffolding of dark matter that binds the galaxy together. The implications are profound. Cosmic rays are not just a curiosity of astrophysics. They have real effects on the solar system and even on Earth. These high-energy particles can penetrate planetary atmospheres, influence cloud formation, and contribute to radiation levels on the surface of planets. If their flow into our solar system is being modulated by galactic structures, then our environment here on Earth is, in part, shaped by events and structures far beyond the Sun. Voyager 2 has shown us that interstellar space is not a calm void, but a place of currents, waves, and hidden influences. Every cosmic ray it detects is not just a particle. It is a messenger from the galaxy, carrying information about forces we are only beginning to understand. As Voyager 2 pushed past the Heliopause, one of its most startling discoveries came from its plasma science instruments. Plasma, the charged soup of particles that fills much of the universe, was expected to behave in a predictable way. Beyond the reach of the Sun's solar wind, scientists assumed they would encounter the cool, diffuse plasma of the interstellar medium, spread thinly between the stars. But what Voyager 2 actually found was something entirely different. The plasma just outside the solar system was far denser and colder than anyone had predicted. It didn't match the signature of the solar wind, and it didn't resemble the interstellar medium either. It was something in between, a mysterious, transitional state, like a buffer zone or sheath wrapping around the solar system. This discovery was profound. For decades, astronomers imagined the Heliopause as a clean border, a sharp dividing line where one environment ends and another begins. Voyager 2 revealed that reality is far more complex. Instead of a boundary, the edge of the solar system behaves more like a shifting frontier, with layers, textures, and pockets of plasma that don't fit neatly into our model. Some researchers now believe this plasma sheath acts as a kind of shield, absorbing and redirecting the harshest radiation of interstellar space. Others suggest it could be the product of dynamic interactions between the Sun's magnetic field and the galactic medium, like two great oceans colliding and forming turbulent eddies. The plasma itself seems to carry signatures of both solar and interstellar origins, as if Voyager had entered a twilight zone between two worlds. This raises a host of questions. How stable is this buffer zone? Does it expand and contract as the Sun moves through the galaxy? Could it grow stronger during certain cosmic cycles, or weaken in ways that expose the solar system to more radiation? If Earth is protected by this hidden sheath, then its long-term changes could directly affect life on our planet, in ways we are only beginning to imagine. Voyager 2's plasma data was especially valuable because, unlike Voyager 1, its instruments were still active and functioning. This meant scientists could, for the first time, actually measure the density, pressure, and temperature of this strange region. What they found did not match expectations. It opened up entirely new questions about how our solar system interacts with the rest of the galaxy. The picture that emerges is not of a solar system floating in a calm void, but of one cocooned in a complex, shifting boundary zone, a membrane that is alive with structure and change. Voyager 2 has shown us that the edge of the Sun's influence is not a wall, but a veil, delicate, layered, and full of mysteries still waiting to be unraveled. As Voyager 2 ventured into interstellar space, scientists carefully analyzed every faint transmission it sent back. But it wasn't just the data that caught their attention. It was the signal itself. The spacecraft's radio messages, normally clean and steady, began to arrive with subtle distortions, shifts in frequency, slight delays, and even faint echoes, as though the signal had traveled through a medium that was not uniform, but turbulent. These distortions told a remarkable story. They suggested that Voyager's radio waves were being bent, stretched, and reflected by invisible structures in the plasma beyond the Heliopause. Rather than traveling in a straight path, the signals seem to weave their way through folds and eddies in the cosmic fabric, much like light shimmering as it passes through rippling water. For scientists, this was a revelation. It implied that the Heliopause is not a sharp, static wall, but a layered, dynamic frontier. Instead of a clean division, the edge of the solar system is textured, made of plasma sheets, bubbles, and waves that shift over time. Voyager's radio signals were acting as probes, tracing out this unseen structure by the way they bent and echoed on their journey home. Some researchers compared it to listening for distant thunder in a storm. The echoes and distortions carried clues about the shape and density of the clouds, even though the clouds themselves remained hidden. In the same way, Voyager's radio transmissions became tools for mapping a region we cannot see, giving humanity its first direct evidence of the Heliopause's complexity. This also hinted at something even larger. If plasma layers and folds exist at the edge of our solar system, they may be constantly moving and reshaping themselves as the Sun and the galaxy interact. Over millions of years, this dynamic frontier could expand or contract, altering the way cosmic radiation flows into the solar system. It might even play a subtle role in Earth's long-term environment, shielding us at some times, exposing us at others. To think that faint distortions in a spacecraft's signal, sent by 1970s technology across 12 billion miles, could reveal the structure of the galactic boundary is astonishing. Yet, that is the power of Voyager 2. Its transmissions are more than just data. They are messages encoded with the fingerprints of the universe itself. In these whispers of distorted radio waves, we are reminded that the cosmos is not empty. It is alive with structure, movement, and hidden layers. Voyager 2 has shown us that the edge of the solar system is not the end, but the beginning of an entirely new frontier, one shaped not by silence, but by echoes. One of Voyager 2's most startling discoveries came when its instruments began detecting sudden, violent shifts in the magnetic field. Instead of the steady background scientists expected, the spacecraft recorded rapid polarity changes, moments where the magnetic field flipped, twisted, and then snapped back into place. These were not random fluctuations. They were the unmistakable signs of magnetic reconnection, one of the most powerful processes in the universe. Magnetic reconnection occurs when opposing magnetic fields collide and realign, releasing tremendous bursts of energy. We see it near stars, where it powers massive solar flares. We see it near black holes, where it accelerates particles to near-light speeds. But to witness it at the very edge of our solar system, in what was once thought to be a quiet, passive region, was completely unexpected. Each time Voyager 2 detected a reconnection event, it was like catching a lightning strike in deep space. These bursts of energy carried implications far beyond the spacecraft's immediate surroundings. They suggested that the Heliopause is not a static bubble, but an active, stormy frontier, constantly reshaping itself as galactic magnetic fields clash with the Sun's own. For scientists, this changed everything. It meant the boundary of our solar system is not just a protective shell, but a region alive with turbulence and power. Instead of simply deflecting interstellar forces, the Heliopause is interacting with them, producing explosions of energy that ripple outward into the galaxy. This raised new questions. Could these reconnection events act as natural particle accelerators, hurling cosmic rays into the solar system at energies higher than we imagined? Could they be shaping the very radiation environment that Earth has evolved under for billions of years? Some researchers even speculate that the cycle of reconnection events may rise and fall with the Sun's own activity, meaning the shield around our solar system is constantly breathing, shifting, and sparking with energy. Voyager 2's detection of these events forced scientists to rethink the outer solar system. It is not a dead zone. It is a place of storms and explosions, where invisible battles between magnetic fields play out in silence across billions of miles. To imagine a spacecraft built with technology from the 1970s, sailing through this battlefield and calmly recording its details is extraordinary. Each burst of data it sends back is a reminder that even in the farthest, coldest reaches of space, the universe is alive with energy. Voyager 2 has shown us that the edge of our solar system is not just a boundary, it is a frontier of power, where unseen forces collide, and where mysteries that shape the galaxy itself are written in the shifting lines of magnetic fields. As Voyager 2 continued its voyage beyond the Heliopause, it began reporting something even stranger than magnetic storms or distorted signals. Its instruments detected wave-particle interactions unlike anything scientists had ever seen. Normally, when charged particles move through plasma, Their behavior follows predictable patterns. They exchange energy in ways we understand, guided by established laws of physics. But what Voyager 2 observed did not fit those patterns. Particles were gaining and losing energy in unusual bursts, as if invisible hands were pushing or pulling them in ways that defied expectation. Waves in the plasma seemed to be transferring energy with an efficiency that shouldn't be possible, creating sudden accelerations and decelerations in particle motion. To researchers, this was a sign that new physics might be at work. Some suggest that Voyager 2 may have encountered an exotic plasma state, a form of matter that exists only under extreme cosmic conditions. Plasma, which makes up over 99% of the visible universe, still holds secrets, and this could be evidence of behaviors we've never been able to reproduce in laboratories on Earth. Others propose that entirely new energy transfer mechanisms might exist in the boundary between stellar and galactic space, where magnetic fields, turbulence, and cosmic rays all collide. If confirmed, these findings could rewrite textbooks on plasma physics. They might also help explain some of the universe's greatest mysteries: how cosmic rays are accelerated to such incredible energies, how magnetic fields shape galaxies, and even how stars and planets interact with the space around them. The implications don't stop there. Plasma processes govern the behavior of everything from solar flares that affect satellites and power grids on Earth to the way galaxies evolve over billions of years. If Voyager 2 has uncovered a new form of plasma physics, it means our models of the universe itself are incomplete. It suggests that the very medium through which light, particles, and energy travel is far stranger than we thought. This discovery also reignites a profound truth. The universe still holds mysteries that challenge our most fundamental science. A spacecraft launched in the 1970s, powered by less computing power than a modern wristwatch, may have just stumbled upon phenomena that hint at unknown states of matter. Voyager 2 reminds us that discovery often begins at the edges of maps, edges of theories, edges of the possible. And now, at the edge of our solar system, we may be witnessing the first signs of a deeper physics that connects the sun, the galaxy, and perhaps the cosmos itself. Perhaps the most breathtaking revelation from Voyager 2's journey is the possibility that it has brushed against truly colossal structures, frameworks on a galactic scale that shape the very environment of stars and planets. The probe's instruments picked up subtle hints of massive magnetic filaments and currents that stretch across interstellar space, like invisible scaffolding holding the galaxy together. These are not small, localized effects. If confirmed, they would represent features so vast that they span light years, guiding the flow of energy, particles, and plasma across the Milky Way. Voyager 2's readings suggest that cosmic rays, plasma turbulence, and even the distribution of interstellar dust are not random, but are steered along these hidden highways of magnetism and current. Imagine the galaxy as a vast cosmic ocean. These filaments would be the currents and tides, unseen to the eye, but powerful enough to shape the movements of ships, waves, and storms. In the same way, galactic-scale magnetic structures could control how cosmic rays travel, how plasma is distributed, and how energy moves between stars. Voyager 2, drifting far from home, may have briefly felt the tug of these immense currents. This idea also connects to one of astronomy's deepest mysteries: the role of magnetic fields in shaping galaxies themselves. For decades, scientists have struggled to understand why galaxies rotate the way they do, how spiral arms form, and why energy seems to move so efficiently across such great distances. If magnetic scaffolding exists on a galactic scale, it could be one of the missing pieces, an invisible architecture that holds the galaxy in balance. Some even speculate that these structures may interact with dark matter, the mysterious substance that makes up most of the mass in the universe but remains invisible to our instruments. If dark matter and magnetic filaments are linked, then Voyager 2's journey may have touched the edges of the universe's hidden framework, a vast cosmic web that connects not just stars within our galaxy, but galaxies themselves across the universe. For humanity, the implications are staggering. Voyager 2 was never designed to study galactic-scale phenomena. And yet, with its aging sensors and faint transmissions, it may have stumbled upon evidence of structures that define the very shape of the cosmos. This would mean our solar system is not drifting randomly through space, but is instead riding within invisible channels, influenced by currents and filaments that stretch across unimaginable distances. Voyager 2 reminds us that even the smallest measurement, a magnetic fluctuation, a particle count, a radio distortion, can reveal the outlines of vast, unseen forces. It suggests that the edge of our solar system is not just a boundary, but a doorway into the architecture of the galaxy itself. Voyager 2's journey into interstellar space has revealed that the edge of our solar system is far from uniform. One of the most startling findings comes from its detection of unexpected chemical and thermal anomalies. The spacecraft's instruments recorded unusually high concentrations of heavy ions, including iron, nickel, and negatively charged oxygen ions, traveling at energies that could not have originated from the Sun. These particles likely come from distant supernovae, having drifted across light-years of space before reaching Voyager 2's sensors. Each of these ions carries a story from the distant past, a fragment of stellar explosions that predate our solar system, silently seeding the interstellar medium with the building blocks of planets and, perhaps, life itself. Even stranger were the dust grains Voyager 2 encountered. Unlike the relatively uniform dust within the heliosphere, these interstellar particles were smaller, irregularly shaped, and coated with unknown materials, possibly organic films or frozen volatiles that have never been catalogued. As these grains interact with magnetic fields and plasma, they can charge up and behave like miniature projectiles, triggering secondary emissions and creating an invisible dance of energy in space. Scientists now recognize this as a new frontier, dust-plasma coupling, a process that may be critical to understanding galactic evolution. Temperature measurements added another layer of surprise. Voyager 2 recorded abrupt, localized spikes and drops in temperature, phenomena reminiscent of weather fronts on Earth, but occurring in the near vacuum of interstellar space. These sharp transitions hint at microscopic shock layers and small-scale turbulence, where energy is concentrated and released over distances as small as a few thousand kilometers. The outer solar system, once imagined as calm and unchanging, is instead a place of dynamic activity, where plasma, dust, and magnetic fields interact in complex and unpredictable ways. These discoveries suggest that the heliopause is not merely a protective bubble around the Sun. It is a living, dynamic interface shaped by chemical, thermal, and electromagnetic forces, constantly evolving as our solar system moves through the galaxy. Voyager 2 is revealing a region of space that is chemically rich, thermally active, and dynamically complex, a laboratory for processes that we cannot recreate on Earth. The combination of exotic ions, mysterious dust coatings, and abrupt temperature fluctuations paints a picture of the solar system's boundary as a turbulent, chemically diverse frontier. This is not empty space. It is a cosmic workshop where the raw ingredients of stars, planets, and possibly life are being mixed, transformed, and transported. Voyager 2's findings challenge our understanding of space itself, forcing scientists to reconsider how energy, matter, and chemistry operate at the very edge of the Sun's influence. Voyager 2's journey into interstellar space is more than a technical achievement. It is a revelation that challenges our understanding of the solar system and our place within the galaxy. Its discoveries have redefined the heliopause, the boundary once thought to be a simple line separating solar influence from interstellar space. Instead, we now know it behaves like a semi-permeable dynamic membrane, reacting to both the Sun's activity and external galactic forces. It shifts, fluctuates, and pulses, showing that the solar system's edge is alive with complex interactions. This new understanding carries direct implications for life on Earth. As the solar system drifts through galactic currents, clouds of gas, and magnetic structures, the heliopause may expand, contract, or warp. Such changes can alter the flow of cosmic rays and high-energy particles entering the inner solar system. Over geological timescales, these variations may influence climate, radiation exposure, and even evolutionary processes on our planet. In other words, Earth's environment is not isolated. It is intimately connected to cosmic events happening tens of billions of miles away. Voyager 2 also teaches a profound philosophical lesson. Here is a spacecraft launched nearly 50 years ago, powered by 1970s technology and a long-decaying radioisotope generator, still transmitting data that overturns modern science. It reminds us that exploration is not limited by age, budget, or computing power. Sometimes, the simplest instruments, traveling patiently across unimaginable distances, can reveal truths that challenge decades of human assumptions. More broadly, Voyager 2 forces us to confront the scale and complexity of the cosmos. We have long imagined the edge of the solar system as calm and static, a quiet threshold beyond which nothing of consequence occurs. Instead, we now see a dynamic frontier, rich with turbulence, energy, and structures that stretch across interstellar space. It is a place where magnetic fields, plasma, particles, and radiation interact in ways that remain only partially understood. Ultimately, Voyager 2 is a reminder of human curiosity and perseverance. It shows that exploration is a dialogue with the unknown, a process of asking better questions rather than simply seeking immediate answers. Each packet of data it sends back sparks new hypotheses, challenges old models, and expands the horizon of what we consider possible. Voyager 2's mission is not just about mapping space. It is about expanding the human imagination. Its discoveries at the solar system's edge reveal that the universe is far more intricate, dynamic, and mysterious than we ever imagined. They remind us that even at the limits of technology and knowledge, wonder thrives, and the cosmos continues to invite us to explore, question, and marvel. Voyager 2's journey reminds us that the universe is far from static or fully understood. At the edge of our solar system, a small, decades-old spacecraft has revealed a dynamic, complex frontier filled with magnetic mysteries, strange plasma, unexpected particles, and hints of galactic-scale structures. Each discovery challenges our model, reshapes our understanding, and opens entirely new fields of inquiry. The probe's findings also connect the distant cosmos to life here on Earth, showing how galactic forces might influence climate, radiation exposure, and even evolution. They reveal that our solar system is not an isolated bubble, but part of a living, interconnected galactic ecosystem. Yet beyond the science, there is a deeper message. Voyager 2 proves that curiosity, patience, and ingenuity can uncover truths far beyond our expectations. Even with 1970s technology, humanity can reach across billions of miles to grasp the unimaginable, to challenge our assumptions, and to glimpse the sublime complexity of the universe. As Voyager 2 continues its silent voyage, sending back data from realms no human has seen, it invites us all to look upward and wonder, what else lies beyond the edge? What secrets wait in the dark, between the stars, and at the boundary of what we know? In the end, Voyager 2 teaches us that every edge is not an ending. It is a beginning, a doorway to new knowledge, and a testament to the endless frontier of human curiosity. If Voyager 2's impossible discoveries at the edge of our solar system blew your mind, don't forget to subscribe and hit the notification bell. Join us as we continue exploring cosmic mysteries, strange interstellar phenomena, and the hidden forces shaping our galaxy, because the universe still has secrets that are waiting to be revealed.